Let's go ahead and take a look at a couple of definitions that we'll be using through the rest of this target. And they can be a little confusing because a few of them sound similar, so I have kind of a helpful way for you to keep them apart and to remember what they describe. So let's go ahead and let's kind of read our definitions here. So every system of equation can be classified according to how many solutions it has. A system that has no solutions is called inconsistent. If you have a highlighter, that might be worth highlighting here. It has no solutions. We call it inconsistent. I typically like to think about that as being impossible to solve. Okay? If we have at least one solution, if it is solvable, that gets defined as being consistent. So I think about can being solved if it's consistent. So inconsistent was starting with an I, and impossible also starts with an I, versus consistent starts with a C, and it can be solved starts with a C as well. But if we know it can be solved, it doesn't tell us if there's one solution or if there are many solutions. And so that's why we have to have kind of a second tier of definitions or terms. So the last two terms come into play if it can be solved. We get to classify systems as being either independent or being dependent. And those two different terms describe how many solutions you would expect to find. So if you have a unique solution, if you have one solution, it is known as being independent. So you have an individual solution. If something has an infinite number of solutions, so they would intersect at a line or all the three planes are the exact same, that would be dependent. So here are my hints. Usually I describe dependent as being kind of the dumb case because there are never-ending correct answers. You could keep listing out correct answers for the rest of your life. You could also think about independent having individual or single answers. That's when it would intersect at one point, an independent point. Dependent situations also have a couple of different varieties, and so it's a little bit trickier to pick those out. But here's kind of the way I think about these four terms. So the first question you have to ask is, can this matrix be solved? So that goes back up to the inconsistent versus consistent definition. If you say, yes, this can be solved, it would be considered consistent. If you say, nope, this is unsolvable, it's giving us something that doesn't make logical sense, that is inconsistent and it's impossible to solve. You can kind of see a couple of the examples down below for things that are inconsistent. Things that would be consistent, though, and they can be solved, we have to go one step further. And so after we answer that, yes, there is a solution of some type, we have to say how many. And so we have two options. One solution, which would be independent, having one point where the planes intersect each other, or having infinite solutions and being dependent, which is kind of dumb that you have more than one answer. Okay? Obviously, one solution looks a little bit like this, versus an infinite number of solutions has a couple of varieties and types. Just depends on the situation. And so you can see a couple of those down below. So let's go ahead and let's try a few examples to see if we can start labeling these different outcomes. Here on the next page, can we use that vocab that we just learned about to determine what types of systems are represented by these different matrices down below? We don't need to simplify them or solve them. We just need to kind of look and see what they're telling us and then use those terms. So the first example, technically we really should be putting our line here, but if you were to write these out as equations, that tells us that 1x, no y's, and 5z's is equal to 2, whereas the bottom equation says 1y plus 3z's equals 1. And if you try to figure out what this is telling us, we can't know an x and a y answer without understanding the amount for z. If I chose 2 for z, well, then I would be able to figure out x has to be this much, y has to be that much in order to get our solutions. But if I chose maybe a different answer for z, a different amount, like 10, X will have to respond according to that, and Y will have to respond according to that, so that we can still equal 2 and still equal 1. If I made these -1 for Z, then X and Y will change even a third time to get these two solutions. And so we are stuck being dependent on knowing the value for Z. So this type of a matrix where we actually have another column of numbers and we don't get that full diagonal that the reduced row echelon form would want, those are considered dependent. So we can get pretty close to the answer, meaning it is consistent. It's not saying something impossible, but after being consistent, it can be solved or simplified down into reduced row echelon form. We would say that this would also be dependent. It's dependent on what value you choose for Z. So that is one style of what an infinite solution system would look like. Choosing 2 or 10 or -1 for our Z's gives us 3 different answers that totally work. Question 13, if we look at that, ends up with an equation that says x equals 5, y equals 3, and then the bottom is just a row of zeros. It says 0 equals 0. And so what should we really think about that? Well, 0 equals 0 is not a false statement, but what we've had is a whole row of work, a whole equation cancel out, which technically means that it was exactly the same as one of the other rows if it was able to cancel out to be 0. And so if we had 2 rows that were exactly the same, that means 2 of our planes were exactly the same. So this is something that is consistent. It can be solved and put down into reduced row echelon form, but this is another example of what a dependent situation might look like. So it's not giving us something that's false. So we're consistent. And dependent means we have an infinite number of solutions. 0 equals 0 would always be true. That's another way to think about that. So if that situation is always true, then we will always have answers for what's going on. Let's look at 14. 14, we have 1x, and we put our line over here. We're equal to 5, so that says something good. This says 1y, and then we put our line here. We're equal to 3, and that says 0 is equal to 7. And if you think about those three things, 0 can't be equal to 7. So that's not true. That would be a false statement. And that's opposed to having 0 equals 0. So we were good through x, we were good through y, but the last equation is not true. And so if we're getting something that's not true, that means it cannot be solved. We would have a problem that is inconsistent. This matrix is impossible. 0 is never equal to 7, and so we have a false situation where 2 of our planes would be parallel, or we have some other outcome where they don't intersect at any point. The 15th question. We have 1x equaling 5, we have 1y eventually equaling 3, and then we have 1z equals 0. And that will trip people up because they think that having 1 equals 0 would be bad, just like we had 0 equals 7. But the difference is that we have z, 1z equaling 0. Any of these variables could equal 0. That just means you're locked onto one of the axes when we go ahead and graph our answer. So 5, 3, 0 would be the location in space where those three planes intersect each other. And so that would actually be a solution. And if we get numbers for all three variables, if it makes sense to have those amounts, and we aren't saying something false, then that is a consistent problem. In addition to being a consistent problem, meaning it can be solved, we have one individual answer, and so we would call that an independent system. Hopefully after seeing these 3 examples, those terms make a little bit more sense. All right, but you always have to kind of go through that flow chart and ask yourself those questions. What's going on? Is it impossible, or can it be solved? And then if it can be solved, are we dependent on anything, or are we independent in getting an individual solution? Let me know if you have any questions. I'd be happy to help, and hopefully that explanation helps those terms make a little bit more sense. We'll catch you guys later. Take care.